to attend these talks, and we're very grateful to all speakers that deliver today this fantastic result to us. But as we announced, we have also an early career researcher who is doing absolutely fantastic in this very competitive space of generative models. Valentin, already Arnold said wonderful things for you. Okay, so Valentin de Bortoli is our next speaker. He's from France, of course, originally, but right now in the US, and he will be presenting his talk via Zoom. We are very thankful to have him. Thank you so much, Valentin. The floor is yours, and we would like to hear your fantastic results.
Yeah, thank you. Thank you, Satialis, and also I really want to thank, well, Dennis as well, just for putting the workshop together. I remember I was part of one of the first one. I think it has been really, you've done a really great job at putting this together. So again, thank you. So yeah, today I'm going to talk about the convergence of denoising diffusion models. So basically, there is going to be some stuff that is going to be not redundant, but kind of overlapping with what Arno has said earlier, of course, because we've worked a lot together. But I'll try to maintain that overlap minimal. Yeah, and what I really want to talk about is maybe how, for I think one of the first time, we have a generative model for which we can actually prove things, which are also very meaningful in the sense that it can help us like build some intuition about the practice. So yeah, that will be the goal of my talk today. If I have more time, then I will also present the some extension of these results. So yeah, I mean, like, again, of course, sorry about these slides, but I just want to remind everyone about what is the goal here. So of course, everything that I'm going to talk about is generative modeling, and the generative modeling in a sense, and why I'm talking about this right now is because it will justify some of the assumptions I'm making later on. So generative modeling can be seen as a sampling problem. So it's a sampling problem where we have a distribution pi and we want new samples from this distribution pi. But where it is a bit different from the sampling that you can see, for example, in applied probability. So for example, what Arnak talked about in the previous presentation, or like all the results that you can see on HMC or that kind of method, is that here we usually don't have access to an unnormalized density. So we trade the information of the unnormalized density for another information on pi, and the information on pi that we have is a set of samples. So we say, okay, I'm observing some samples from pi, and I want to get new samples from pi, right? So then these set of samples from pi is for the dataset. So okay, so far nothing new here. But it will, this distinction between the sampling as we understand it in statistics and the sampling as we understand it in machine learning and generative modeling, I think is important to specify the kind of assumptions that we're willing to make on this distribution pi. And so, yeah, I mean, like I just want to present one general approach to do generative modeling, which is the one which encompasses, I think, all existing models. And all existing models, we can think of them as first sampling from what we call a reference distribution, so pi naught, so which can be, well, usually it will be a Gaussian. And then you just modify it with some mapping, G. Note that this mapping, I'm not saying what it is, and this is why this slide is, I mean, very general, but also very not precise, is because this mapping G is the one that is tasked of pushing pi naught into pi, the generative model, right? And of course, G is very complicated because G must go from, well, must push a unimodal, nicely behaved Gaussian distribution to something that can be as complicated as you want, sorry. And what will happen in practice, of course, is that G is going to be learned with the training data set. And when I say mapping, this mapping G, it can be stochastics. It can be basically whatever you want. And in particular, if you think of the mapping G to be the diffusion that Arno talked about when he introduced diffusion models, then this mapping G can also be thought of as a process, right? Like you can think of a stochastic process. If you have a strong solution, you can think of it as a function that takes the Brownian motion as an input. Okay, so this mapping G really can be whatever you want. The important thing is that it pushed the Gaussian distribution to the generative modeling distribution. Anyway, so that's the kind of model I'm going to have that I'm going to look at. Of course, I'm going to be focused on diffusion models because I can say meaningful fields here, but I just want to emphasize that actually, if you want to have a global approach to generative modeling, that's the kind of thing that we are looking at here. And another example, so Arno talked a little bit about Riemannian diffusion model, or Riemannian generative modeling. I just want to emphasize here that we actually have a very good application of generative modeling that comes from protein modeling and from biology. The reason for that is that why I'm putting this example here is that if you look at generative modeling paper, most of the time they focus on images, maybe text, maybe sometime audio, and now more and more video. But it's hard to know if these models are useful besides producing very good looking images and yes, text to image and stable diffusion is very nice and it's fun and everything, but do we have actual application in science? And the answer is yes. And I think that's also part of a very strong motivation for generative modeling. So I'm not going to dive into the detail here. I can answer more questions if they are at the end of the talk, but the task that I want to solve when I do protein modeling is I want to go from a sequence of amino acid to a 3D structure. Okay, so a sequence of amino acid is just a sequence of letters. So for example, A, B, D, G, etc. And each letter represents a specific amino acid. And once you have a sequence of amino acid, it fully characterizes your protein. So I have a representation of the protein as a sequence of letters. And now I want to get the 3D structure that is associated to that. Why do I want that? Well, it's because actually the 3D structure is what is going to determine the shape of the protein, and the shape of the protein is how the protein interacts with its environment. So for example, if you're looking at if you want to build a new antibody, if you want to build a new vaccine, the 3D structure is hugely important. And we know that there is a kind of a one-to-one mapping between the sequence of amino acid and the 3D structure. So one goal would be to get the sequence of amino acid and then get the 3D structure. So this can be done experimentally. Turns out that if you do that experimentally, it's really a arduous task, in the sense that usually it will take one PhD student or one postdoc to synthesize one protein. So it is very expensive. The techniques that go there is absolutely mind-blowing in the sense that everything is very, very super precise. And so there is now the obvious machine learning question that comes with it, which is, well, if you give me the sequence of amino acid, because the sequence of amino acid is kind of easy to get, if you give me the sequence of amino acid, can I give you the 3D structure? And it turns out that this is a problem that is kind of well suited for machine learning because we have access to a ton of data. Well, a ton. We have access to quite a large amount of data on that. So there is, for example, a website that is called PDB, the Protein Databank, where you have a bunch of proteins with their sequence and also the 3D structure. So you could imagine learning a model that, given the sequence of amino acid, is going to give you a model of the 3D structure. So you can see that you can recast this problem of protein modeling as a generative modeling problem. And once you have this generative modeling problem, then you can apply all generative modeling techniques to try to solve this. So of course, I'm telling that, but you might already be familiar with with this paper by Senior et al., which is called AlphaFold, and kind of revolutionized the field of protein modeling. So again, I think that this is one of the very important implications of generative modeling, was that when we input some kind of conditional information, so not only generative modeling is good for unconditional, image synthesis, but also very useful in science if you put some kind of conditional information. So here, the conditional information is the text, the amino acid sequence, and we are working on generative modeling on the space of 3D structure of protein. Turns out that during the 3D structure protein, generative model requires us to work on Riemann and manifold. So maybe I will touch a word about that later on. But yeah, that's kind of the motivation I really want to put forward, because I think it's also why there is such an excitement about generative model in the machine learning literature. Okay. So of course, again, I'm not going to dive too much into this slide, but just to tell you, kind of put denoising diffusion model into the literature. So there has been, again, this huge excitement on generative model for the past 10, 15 years, even more maybe, with a very recent acceleration during the past 2 years. And of course, you might be familiar with variational encoder, so VAE, energy-based model, also called EBM, generative adversarial network GANs, normalizing flow. I'm not going to talk about that. I'm going to focus on denoising diffusion model. But again, I want to say that denoising diffusion model can be recast in some version as a specific case of normalizing flow. It also has link with variational encoder. So that was the work of Jonathan O in denoising diffusion probabilistic model. And it also has link with energy-based methods. So while these methods are initially being introduced in very distinct ways, you can draw edges between all these vertices here in this graph. And while there are a lot of models, I think a lot of them can be seen in the same light. But today, again, I'm going to focus on denoising diffusion model, and I'm not going to focus on the properties of the transformation. So remember, I was talking about this mapping G earlier, the one that brings the Gaussian data to the data distribution. Turns out that if you focus on this mapping G and its properties, then you are dealing with optimal transport, then you are dealing with stochastic control. And this is very much linked with the Schrödinger bridge stuff that Arno introduced, talked about earlier on, which I really would love to talk about. But today I'm going to focus on something else, which is kind of the kind of theoretical result that we can get for this generative model, for the denoising diffusion model. And maybe if I have the time to dive into a little bit more into the extension to the Riemannian setting, because the Riemannian setting is also very important for us. Okay. Okay, so again, the next two slides are I'm going to go very fast on these ones because Arno already talked about that. But denoising diffusion model, how do they work? Now you know how they do. You start from the data distribution. You have a forward noising process that you can write. You can decompose the Markov chain like this with a forward decomposition. And if you look at the trajectories, it's just destroying the data and completely noising it. And then you can look at the backward decomposition that is exactly the same chain, but reversed in time. And when you reverse it in time, then you start from noise and you go to data. Okay, so that's again the principle here. And how to go from a forward decomposition to a backward decomposition, that's called ancestral sampling. Okay. Again, I'm going to go quite fast on this slide too, but the big question is, how do we compute this backward decomposition? And to compute the backward decomposition, you can first use the bias rule to express the backward kernel. So pk given k plus 1 as pk plus 1 given k, and the ratio of density here. Of course, since you have the choice on how you're going to choose pk plus 1 given k, usually you choose it Gaussian, like Gaussian and linear, to destroy the data. So actually, this is a very vanilla kind of, preliminary discretization of the Wasserstein-Lebesgue process. And then once you have this ratio of density, of course, the whole thing is not Gaussian anymore, but you do your kind of Taylor expansion, as Arnaud explained, and you recover that pk given k plus 1. So sorry, there is a typo, that's not equal, is approximately equal to this background process, right? Okay, and now there is the task of estimating the score that appears here, so which is the grad log of pk plus 1. Of course, pk plus log of pk plus 1 is not tractable, as Arnaud was saying, because it would require you to know P0, and P0, remember, that is the data distribution, okay? But instead, what you can do is have another form of grad log pk plus 1, because grad log pk plus 1 can be written as the conditional expectation of grad log pk plus 1 given 0. It turns out that grad log pk plus 1 given 0 is completely tractable because you are conditioning on time 0. So this whole thing is Gaussian, and I can compute it quite easily. Of course, there is something that is going on here, and the thing that is going on is that here I have a conditional expectation of what happened at time 0 given what happened at time k plus 1. And of course, I cannot compute that, because if I were able to compute this, then the whole thing would be tractable. And if the whole thing is tractable, then I have access to the score, right? So now the question is, how do I compute this conditional expectation? Well, it turns out that you can remember that this conditional expectation is in fact a solution to a minimization problem, because as every conditional expectation is under mild integrability assumption. And if you do this, then you can rewrite this grad log of pk plus 1 as the minimization of this loss function here. And then this is the only place where you actually use deep learning or any kind of neural network parameterization, because now this is your loss function. So you actually have one for every k, if k goes from 0 to capital K or capital N here. And so you can train your neural network. And once you've trained your neural network, that's it, you're done. You replace the grad log pk plus 1 here by sk plus 1, and that's it. Okay, so that's, again, that's very, I've gone very fast through the basics of diffusion models, but that there is nothing new compared to what Arnaud had said earlier. Something that will be hugely important for me in the rest of the talk is the fact that, again, also Arnaud said that, the fact that you can put aside the dirty Taylor expansion that I have done, but instead you can just look at it as a time reversal. So you had a forward process. So the forward process will be denoted xt. The forward process was noising the data. And then what you consider is a backward process. So yt, which is given by x capital T minus t. And the question is, does this also satisfy a stochastic differential equation? So when you think about it, I think that's a very interesting fact that you have something that diffuse forward. You look at it backward, and the question is, does it still satisfy an SDE? And I think the fact that the answer is yes is kind of surprising. So of course here, while I'm not detailing what is the filtration that is associated with this backward process, so this is the reverse filtration, just for the technical detail. But it's in fact a very general result that if you have a process of some type, you have that the backward process will also be of the same type. What I mean type here, like for example, if you have a diffusion, you can recover that the backward process is also going to be a diffusion. But for example, if you have a jump process, the backward process will also be a jump process as well. So the first result, I think, were found by Anderson in 1982. Also, there is a very nice extension by Osman and Pardue for general diffusion in 1986. But you have like very recent results by Patrick Catio and co-authors from 2021, which give an abstract setting for this type of time reversal formula, which covers a lot of stochastic process. So what I'm saying here is not only true for diffusion, but it's true for other processes as well. And it turns out that, of course, if you look at the Euler-Maruyama discretization of this thing, then you recover what I was talking about earlier on. You see that you have your score here, and you have the y.t here that corresponded to this term before. Okay, so that's kind of the gist here. And yeah, what I'm going to talk about today is more really the theoretical results, and like how do we get this type of theoretical result. So in the first paper that we had with Arno, James Thornton, and Jeremy Eng, it was a paper on Schrödinger bridge, but also while we were looking at it, we provided the first results regarding the convergence of diffusion model. So I had to make a bunch of assumptions here, which I'm going to argue were not very good for generative modeling. So the first assumption is the fact, and maybe the strongest one, is the fact that the score is uniformly, the score approximation, so ST, is uniformly closed from the grad log PT, uniformly closed in space and in time. So that here is what I could say is the deep learning belief, right? Because there is kind of no way you can, in practice, control this fact, because you obtain ST as the minimizer of some function. I know that if the minimizer is the exact minimizer, then I have that ST is equal to grad log PT. So if this was true, then yes, I will have this thing equal to 0. But of course, I have no control over this. And what I need to do is to be able to control that, which I'm not going to dive into this. There are a few papers that actually try to control this error here. Okay, another very strong assumption that we make in this that I made in this work is an assumption of the data distribution. So the data distribution pi here, I'm going to assume that it admits a density with respect to the Lebesgue measure, and that the gradient of the log of this density satisfies this kind of condition. So if you've worked on the convergence of Langevin algorithm or the convergence of diffusion, you know what is that kind of condition, and this kind of condition is a contraction at infinity. So basically, I want my model to have a drift that is going to pull back all the points that go to infinity. And this is typically the kind of condition that was, for example, considered by Andreas Eberle when he provided, well, it's kind of a little bit different condition than the one that was considered by Eberle in his 2016 paper, where he deals with the convergence of diffusion. But anyway, that's the kind of assumption that I'm going to make on pi. And under these two assumptions, what I have is the following result, which is that if I look at in total variation between pi and pi hat, where pi hat is my model. So pi hat is the model I have with the denoising diffusion model. So really the output of my algorithm. If I look at in TV, so total variation, I have the term can be split into two parts. The first part is exponential minus t. So again, that's the convergence rate of the Lebesgue process. And you have a second part that depends on the discretization step size that I call gamma and the score approximation m. There is an exponential t here that does look bad. I just want to point out that this could be actually hugely improved. And the reason it's here is because the first time I wrote the paper and the first time I wrote the result, I did a kind of a bad manipulation of a Grunwald lemma. And so this dependency here could be actually much improved. But yeah, that was kind of the first result out there on diffusion model. And then that was kind of partly motivated by some work by Yakiv on the behavior on diffusion model under the manifold hypothesis. Something that is quite non-realistic in the assumption that I've made so far is the assumption on pi. Because the assumption on pi so far is that it admits a density and that I have this kind of recall at infinity, which is never going to be true for us because I cannot check what is the density of pi, right? It's kind of different from the context of statistics where you have a normalized density. And as Arnak was saying, for example, to enforce this type of condition at infinity, I can just add some kind of extra, quadratic regularization. I mean, if grad log p of x is not too badly behaved. But here I don't have access to that at all. Like I just know pi through the samples. So I cannot, making this type of assumption, in my opinion, is a bit too strong. And also there is this type of hypothesis that we make in image processing, which is that the data is actually not supported on the whole space, right? Because if you have an image 256 by 256, and if you look at the images of cats, you kind of expect the images of cats not to be something that is 256 by 256 dimensional, right? That is, this 256 by 256 dimension is not specific to cats. It is something that is specific to the resolution. So in fact, what you have in mind is that these images of cats are supported on a lower dimensional manifold. So an hypothesis that would make more sense, and is the one that is sometimes called the manifold hypothesis, is the fact that pi is supported on a compact manifold. I'm dealing with compactness here, compact manifold, just because, well, it also makes more sense since, of course, the value of the image and like the value of the pixel are going to remain bounded, especially when you look, since I have access to pi only through the empirical measure. Well, some empirical measure and some samples. Okay, so that's the type of assumption I'm making here. And under this assumption, what we have is we still have to assume some kind of discretization error, approximation error of the score. And under this type of assumption, we have the same result, but in Wasserstein 1. And that's the result I'm going to dive into the presentation of this result now. So this is the full result. So when I say under the manifold hypothesis, I'm going to describe what it is exactly. I'm going to describe all the assumption in the next few slides, but this is the result. So the result you can see is actually very similar to what we had before. You have the discretization error with M, you have the step size error with gamma, and you have the exponential convergence exponential minus t, which is still the convergence of the Wasserstein and Lebesgue process. You have an extra parameter beta. I'm going to talk about what it is. It's simply the speed of the forward process. So you can think of beta equal 1, and that would be fine. But maybe the most interesting parameter that I have here is this epsilon. So I have this epsilon dependency, and this epsilon dependency is simply because now, when you think about it, let's say that your data is supported on the lower dimensional manifold. If I go backward in time, there is no way that I can compute grad log pt for t equals 0. Why is that? It's simply because because P0 represents the density with respect to the Lebesgue measure of the data distribution. So that means that since here I'm supporting on the lower dimensional manifold, I cannot say that I have a density for the data distribution with respect to the Lebesgue measure. I could do that, for example, with respect to the R measure of the manifold, but I don't know what is the manifold. So if you look at it through the lens of the Lebesgue measure, this type of quantity does not exist. And what you will see in practice, and I have a picture of that later on, is that the gradient of the log of pt actually explodes near time 0, right? Because since your density is more and more concentrated, then the gradient of log pt explodes when you reach time 0. So what people have been doing in practice, and what I found is also necessary to do in theory, is to stop the backward process at the time epsilon. So instead of going all the way, you just stop at the time epsilon. And that way you don't have this kind of degeneracy in the score. So now instead of having 2 terms, we have 3 terms. And the last term is really specific to the fact that we have assumed that we have some kind of manifold support here. Okay. So yeah, I think here that the dependency in epsilon is not good, especially we have this exponential dependency. I really think it could be improved. I've not managed to do it so far. I mean, under, for example, some kind of geometric assumption on the manifold, let's say if it's convex, if the manifold is convex, then you can improve this dependency, this exponential dependency. But so far, I haven't found like a very, very compelling geometric argument to completely remove this term. So yeah, that's maybe one of the bad dependency that can occur. I also want to comment on the constant d0 here. The dependency with respect to the dimension of the ambient space. So let's say the dimension of the image is simply, I think, quadratic in my paper. It's not at all exponential. We only have this a dependency which is at most quadratic in D. What is important is the notion of diameter of the manifold that appears. There is a compactness assumption here for my data. Usually the diameter of the manifold is a quantity that we are okay with, I want to say, in generative modeling, because we can always rescale the data. It would be even better to obtain results with respect to the intrinsic dimension of the manifold. So this is another line of work that I think is quite promising. It requires to change a little bit the analysis, but you can obtain results where you change the definition of kappa, and kappa can be replaced by something that's going to depend on the intrinsic dimension of the manifold. Anyway, so before I dive into the presentation of the results here, I just want to say that there have been like many extensions of improvement of this type of results. I'm not going to talk about them too much, but yeah, please feel free to ask questions about this. So again, I talk about the manifold hypothesis. So it's the fact that we are not supporting on the whole space, and for that reason, the total variation distance does not even make sense, right? Because the pi hat, what we generate, is going to be supported on the whole space just because we add Gaussian noise at every stage. So if you look at the distribution of pi hat, this is supported. This has a density with respect to the Lebesgue measure, but we know that pi does not. So in fact, if you look at what happens under the manifold hypothesis, you always have in total variation, you have pi minus pi hat, which is equal to 1 in total variation. And that is because in order to look at the total variation, you really need to be able to compare the densities. So this is sometimes called a vertical distance, in the sense that you are looking at comparing the density. And what I think makes more sense in our case is to look at what we sometimes call horizontal distance, because horizontal distance, like Wasserstein distance, they look at what happens in terms of sample. So for example, like in this in this too small graph here, I have presented what is the distance between two direct measures in Wasserstein 1 and in total variation as the distance between the two direct increase. So of course in Wasserstein 1 you just have the classical Euclidean norm, and in total variation is the L0 norm. So the total variation is not sensitive at all at how close the sample are, which is kind of the thing that we are expecting to look at here in terms of manifold hypothesis. Okay. That justifies why I'm looking at the Wasserstein distance here and not the total variation. So if I'm briefly describing the assumption I'm making now, I'm still making an assumption on the score. So this is the thing that I'm not going to discuss too much here. But this assumption is that the score explodes both spatially and it explodes also in time, because the sigma t here, it goes to 0 at time 0. This is an assumption that you can verify even experimentally. And it allows for an explosive behavior of S theta. So you're still saying that, okay, my score approximation is relatively close to grad log PT. So clearly this could be, this might not be true if your network is not good enough, but I'm still allowing it to explode near time 0. Okay. And you have like other, I want to point out that this is a L infinity assumption. There has been work on deriving L2 errors in these two papers, for example. Okay. The last two assumptions I'm making is a slight modification of the Lebesgue. So the forward process I'm looking is in fact this process. So it's the same as the one I had before if I'm willing to say that beta t is equal to 1. Because if beta t is equal to 1, then I recover my classical Lebesgue. But in practice, people do consider this speed here, this beta t, that depends on t, and that is much for practical reason. But turns out that the results I'm going to present actually generalize to if you can put this beta t here, and these assumptions on the beta t are actually quite mild. If you are willing also to make some kind of assumption on the size of the step size that is going to be linked with beta, then you have the whole list of assumptions I'm considering for the results. And I want to, before I conclude, I want to give a proof of this result and kind of the sketch of the proof of this result. So first, if we were to go back to the total variation, right? The total variation result that I had. So the total variation result that I had, I have a very simple decomposition. So the law of x naught, which is pi hat. So so I'm looking at the difference between pi hat, so the law of x naught, minus pi in total variation. I can rewrite that as pi infinity, where pi infinity, sorry, here I should have said is the Gaussian. This is the Gaussian. And here I have applied the iterated kernel n times, where this is the iterated kernel, which is associated with the backward Markov chain. Okay, so this is just a simple definition. Now, what I can write is, well, actually pi is pt, so the endpoint of the forward Lebesgue, and then I apply qt, where qt is the backward Lebesgue. So here, what I've simply said is that pi is the same thing as starting from pi, going forward in time up to time t, and then going backward in time up to time t. This is exactly what is written here in this line. And now what I can do is I can split this term just using the triangular inequality. I'm replacing pt by the Gaussian measure, and that's how I end up with these two terms. If you look at the first term here, the first term is simply a discretization error. So because you know that Rn hat is trying to approximate qt, and they both start from the same measure, then I'm just comparing it's like, you know, when you look at the difference between the distance between a stochastic process and its discretization. So here it's every technique that you know to control discretization error can be applied here. So for example, I use the Girzanov theorem, which is very similar to something that, for example, Arnak has already used and studied. And for the other part, well, the other part, we use the fact that the total variation is always contractive with respect to, one Lipschitz with respect to the application of a kernel. And so what I end up with is that I can rewrite this simply by removing the qt, and this is simply pi pt minus p infinity. And this second part here is simply the difference in total variation between the Gaussian and pi pushed by pt, and pt being the Lebesgue kernel. So this is just the convergence of the Lebesgue kernel. So that's why Arno was saying that the convergence of the backward is in fact inherited from the convergence of the forward. Of course, now we have this complicated discretization term to deal with. Okay. So if we look at now what happens for the Wasserstein one, we can do exactly the same decomposition, except that we do not go back up to time 0. We go back up to time tk, where tk is there is a mismatch of size epsilon, just to avoid the degeneracy. So that's why I have an extra term, and this extra term here, pi p t minus tk, is basically going to handle this degeneracy near time 0. And yeah, and so the discretization, so I'm going to tell you how I deal with the discretization term. The convergence term is dealt with exactly like you would do for for the as you would do with the Lebesgue process, and the non-degeneracy term is also quite easy to deal with. So what is not easy to deal with is the discretization. Well, one of the terms that is a bit different to deal with is the discretization. You could use some kind of Gaussian theorem here. I was trying not to apply that. Part of the reason for that is because you could replace the scheme that we have to sample from by something that is deterministic, in the sense that we know that there is for each SDE, there is an associated ODE that is the same marginal at every time. And there has been some very recent work on how to analyze that. And you cannot do this with the Gaussian theorem, because the Gaussian theorem, it requires the two processes to be driven by the same Brownian motion. Of course, if one of the processes is deterministic, then, well, there is nothing to look at, because one of them that just does not have a Brownian motion. So instead of relying on the Gaussian theorem, I'm relying on an interpolation formula that was formulated by Pierre Delmoral and Singh, which is simply something that is going to tell me what is the difference between two processes. So here you have the top process is the real stochastic process, and the bottom process is the discretized one with the score approximation. And it turns out that you have an explicit formula for this, which is given in terms of tangent process. So it relies on the theory of stochastic flow, but this is an exact equality. And now I just have to, it relies on some coupling, of course. So here, this is the uniform coupling between y and y bar. And based on this uniform coupling, what I'm going to see is that the difference between these two processes is actually driven by delta B, and delta B here is just the difference of the drift. So provided I have a uniform control of the tangent process, I can control all this stuff. And that's what I use in this result. So there is some work to control uniformly this tangent process, but once this is done, then this is a very easy approximation to do. Okay, and once you have it, you have the whole result here, which again I just want to highlight before I stop. The result that we have here is a result that tells you that in terms of convergence, you have something that converges as fast as the Lebesgue process, but you have to pay the price somewhere, and where you pay the price is actually in this approximation m, the approximation constant m that we have here, which is something that is kind of based on our belief that deep learning is working and that I have a good approximation for my score. But in practice, this is something that we cannot really control. And I think that if you have any bad dependency with respect to the dimension, any bad dependency, with respect to the constant of the problem, this is not going to go inside the convergence rate as it would do in a classical Langevin setting, or any kind of HMC type analysis of the convergence. It will go in the discretization error here. So I think that's kind of the take-home message here, is that whatever the analysis that you do for this denoising diffusion model, you are kind of trading off the convergence, a good convergence rate for a bad discretization. But at the same time, another take-home message I want to convey here is that I think that the kind of setting that we are usually exploring in diffusion, in statistics. So for example, the assumption that we have Poincare inequality, the fact that you have a logarithmic Sobolev inequality, is not exactly the setting that we want to look at for generative modeling, where some assumption as the manifold hypothesis would make much more sense here. So yeah, I mean, that was my attempt at explaining the result. I will skip on the Riemannian part, which was just a presentation, a little bit deeper presentation of the Riemannian setting that Arnaud has briefly talked about earlier. And instead, I'm just going to conclude here by saying that I think there is really an opportunity here for practitioner and people who do theory on this type of process to actually understand what's going on, because I'm not claiming that the results I obtain are exactly what is happening. Quantitatively, I don't think I think the bounds are still quite loose, but I think they are quite informative. At least for me, they help me understand how this type of diffusion model work and what quantities are important. So I think that's a nice area, and there are of course a lot of things to be done at the intersection between theory and practice here. I just want to highlight that something I didn't talk about at all is that here we are looking at things that converge in finite time. So if everything was perfect, we would be converging in finite time. And for that reason, I think that we might be able to use tools that come from optimal control and optimal transport instead of sampling, because sampling usually we assume that the time that we have to wait is very, very long, whereas here, especially if you look at Schrödinger bridge, we are really trying to find something that converges in finite time. So we are closer to having some kind of control and trying to obtain bounds on this control than trying to wait for the convergence of some Longchamp process. Yeah, so on that note, I think I'm gonna stop. And again, I want to thank you for giving me the opportunity to talk here.